So example number 5, it says given f of x. And you said, well, Mr. Adams, yesterday you spent so much time talking about a function and a vertical line test, and now I see 3 different expressions, and what does all this stuff mean, piecewise function? Well, what it means is that we're setting up different mathematical relationships for different domains. And if we put all of the domains or all these mathematical relationships together, it forms a function that will pass the vertical line test. So sometimes Mr. Adams will talk about a relative domain. So for example, for any value of x that is less than 0, we will determine the mathematical relationship of y as being the negative value of x. For any value of x between 0 and 1, including 0 and 1, we would consider the mathematical relationship of x squared. For any value of x greater than 1, we would consider the mathematical relationship, which really isn't a relationship, it's just 1. Okay? So now how this would look is if I were to make a table of values, and I'm not going to do every single number you could think of. If I were to make a table of values of this piecewise function, and I pick a number less than 1, we'll do negative 1. I would evaluate that negative 1, in other words, x equals negative 1, I would evaluate that as negative x or negative 1. So then my output, f of x, is equal to positive 1. Does that make sense? No?
Yeah, you're putting negative 1 and 2.
Let's go to a different boundary. So what I'm saying is for all values of x
because the negative
less than 0, I'm going to plug it into this mathematical relationship of negative x. Okay? So now, let's pick a number between 0 and 1, including 0 or 1. So if I plug in 0, now I'm going to use this expression. So if I let x equal 0, then the expression that I'm going to use is going to be x squared, which is equal to 0 squared, which is equal to 0. Okay? Does that make sense?
Why do you do 0? Is it because it says we're equal to?
What's our value for x?
No, she's asking why you like 0 for x.
Is it because that it says 0 is less than or equal to?
Yeah, so watch, let me go through this, and then what we'll do is we'll just randomly pick a number and you determine which expression we choose. So next, if I were to plug in 1, if I said x equals 1, I would plug that into what function?
1 squared, or x squared.
Yeah, so x equaling 1 falls in this category, or that domain, relative domain. So then I would say if x equals 1, I will plug that into x squared, which would be 1 squared, which is f of x equals 1. Now, let's pick a number greater than 1. Let's pick the number 2. Now, what I would like for you to do is look at these relative domains and tell me, where does 2 fall? Where does x equal 2 fall?
Greater than 1.
Greater than 1. So when x equals 2, my function is 1. So then f of 2 is equal to 1. Okay?
Why wouldn't you multiply the 1 by 2?
Where do I plug in the x?
Yeah.
Does that make sense to you guys?
Yeah.
So now for a piecewise function, if we were to graph this, it would kind of, let me show you what this would look like. I'm going to sketch it or freehand it. From all x values, so this is our function. When x is negative 1, what is the function evaluated at? Well, that's the one we wrote down. And
Yeah.
so what we're going to do is, let me do it like this. From all values less than 0, this function here, f of x, is represented by the function negative x. Now from 0 to 1, it's represented by the function x squared. So that will kind of look like this. And so let's use a different color, or I'll highlight it so you guys can see. So from here to here, this function, or mathematical relationship, is evaluated at x squared. Now for all values greater than 1, I have x or y equals 1, which is just a horizontal line. So this would be f of x is equal to 1. So now on each one of these, let's define the domain. So here, the domain is x is less than 0. For this little purple section, we would say that 0 is less than or equal to x is less than or equal to 1. And then for this function here, we would say for all values of x greater than 1. Now, if I do a vertical line test on that graph, is it a function? Yes, but how many mathematical relationships are in that function? 3. So in the real world, when we use mathematics, it doesn't turn out to always be a pretty little function. It doesn't always turn out to be a nice little quadratic or a nice little linear relationship. Sometimes it's a combination of functions. And so if we want to study the change of those functions, we can break it up into separate little functions. And that's what a piecewise function is. Does anybody have any questions on that? This is kind of tough to kind of wrap your mind around, but don't worry, we'll do a lot of this stuff. Okay? Let's move on to number 6. If you guys don't have any questions, we'll move on to example number 6. Example number 6 says writing formulas for piecewise functions. Your book says formulas, and that word's okay. But sometimes you might want to think of the word expression or relation. We'll talk more about that in a little bit. But basically, we're going to plug stuff in. So, and when we plug stuff in, we usually use the term formula, but it may be written as a relationship, it may be written as an expression. And so in example number 6, they give us a graph. And this is 0, this is 1, and this is 1 up here. And so this function as we look at this graph, does that pass the vertical line test?
No, because if you were to go through that open point, I'm gonna hit the.
It's not defined here, but it's defined here. How many times would it cross? No, this is nothing. That's why we don't close the circle in. Well,
It means at that point it doesn't actually add 1, 1.
yeah. So let's look at the domains first. Okay. Clearly, there are 2 relative domains in this behavior. All right. The first one deals with, is x defined here at 0?
Yes.
So the lower boundary would be 0. We can include 0. Now what's the upper boundary?
It's 1, but it doesn't equal 1. It's anything up to 1.
Okay, so that's that first line. Now the second line, if we look at the domain, it starts where?
At 1.
Does it include 1?
Yes.
And where does it end?
2.
2. All right. Now, the vertical line test, or the definition of the function, is that there is one unique relationship, right? Is there one unique relationship? In other words, is when x equals 1, is it defined only once?
Yes.
Yes. So if I draw a vertical line test, so just so you guys can see it, if I draw a vertical line right through here, technically it only crosses one time. If I draw the line just a little bit to the left of that, it'll cross only one time here. And if I draw a line a little bit to the right of it, it will only cross one time there. Now, what's throwing us off is that this is a jump discontinuity, which you guys aren't familiar with yet. And you guys are used to seeing functions as like a continuous curve, and we'll talk about that eventually. But this is definitely a function. So now how do I write this as a function, as a piecewise function? Well, what we do is we start with the domain. So I would say that the total function f of x is equal to, okay, let's start with the domains. My first domain is x is, or 0 is less than or equal to x is less than 1. And then my second relative domain is 1 is less than or equal to x is less than or equal to 2. Now, if you study that behavior, there's two different mathematical relationships that represent the lines that we see on the graph. Well, the first one is what function? This first one here is f of x equals x.
Juniors M through Z, juniors M through Z.
Now here's the tricky one. What is the slope of this function? So we have f of x is equal to 1x, but what would the y-intercept be?
There isn't.
Well, if we were to extend that, where would it cross at? Take a guess.
Negative 2.
It'd cross at -1.
It crosses at -1, right? Because if the slope is 1, we can go over 1, down 1, which would put us at -1. So this is plus -1. So this mathematical relationship that represents the second line segment is really x minus 1. Any questions?
Oh,
All right. Let's move on to example number 7, shall we? Yeah. Yes, Mr. Adams. We would love to move on to example number 7.
Super.
Now the reason Mr. Adams was able to actually get the answer for that is I'm used to doing transformations. Technically what we had on that last graph was two functions or linear functions. They're straight lines, and that's always represented by y equals mx plus b, and the b is a vertical shift. So if I know how to transform a parent function into another function, that's how I can map a mathematical relationship to raw data that I see on a graph. So if I have an absolute value function, if I were to consider the function of f of x is equal to the absolute value of x minus 2 minus 1. Now put a star on this one, because this little issue of absolute value functions comes up time and time and time again. If I were to graph this function, Absolute value functions always come to, what, does anybody remember the fancy word for where they come down to? It's like a vertex, but there's another word that we call that.
Minimum.
It's a minimum as well. But in calculus, we consider it to be a cusp.
Oh, yeah, they're talking about that. I was like, okay.
Yeah, it's a cusp. Now here's the thing. When we go to do calculus on this, we can't do calculus at the cusp. I don't want to go into all the details or explain it to you guys, but we can't. But we still want to be able to determine or study the behavior of this portion of the absolute value function, and we still want to study the behavior of this portion. So could I do that? Well, think of it like this. If I take this piece of paper, could I study that? Is that a function? Yeah. Could I study that? What about now? Could I study that? And if I study it in that way, I don't have to worry about the cusp, which by definition I can't really do any calculus on. So what I could do though is make this a piecewise function. So again, we look at the domains. What is the first domain to the left of the cusp?
To which side of the class?
A negative
This side.
infinity to
And to the right side?
to positive infinity.
And so one of these could be less than or equal to, but we can't have both. So this right here is something that we could decide on and talk about later. Okay, this is not necessarily in your notes, but I want to keep it in your brain. We're going to have to keep talking about this notion of taking these functions or mathematical relationships and breaking them up into stuff we could work with, because that's what calculus is really about. Okay, but example 7 asks us to find the domain and range of the whole thing. Is it defined at 2? In other words, if I make this less than and I make this equal to, is there a point in which it isn't defined in the x direction? No. No. So then I would say the overall domain of f of x is what?
Negative infinity to positive infinity.
Negative infinity to positive infinity. And if I were to consider the the range, I'm sorry, the total range of this thing, which is based on the domain, what would you guys say?
Negative 1 to
Negative 1 to infinity. Are we including negative 1?
Yes.
Yes.
Wait, how
So we would say negative 1 is less than or equal to x, which is less than infinity. Now I just want to point out there's a couple ways that you could write it. For the domain you could write it this way, but you could also write it negative infinity, comma, infinity. Put that in parentheses. It's unbounded or infinite. Right, we talked about that earlier. And this one is bounded, so this one would have a bracket, comma, infinity.
How did you get the negative 1?
Oh, because this right here is the lowest value for y.
Oh,
I didn't write it down, but this is negative 1 in the y direction, right? So now when we look at that, a piecewise function is kind of like a composite function. We're putting two functions together. I suppose if we were to write this function, what is the slope of this? Negative 1, right? So this would be negative x. What is the y-intercept? Positive 1, right? So this right here would be negative x plus 1. What's the other part? This part right here. Well, the slope is positive 1, and what would the y-intercept be?
Negative 2?
It's actually negative 3. Does that make sense? Now, later on, what we'll learn is that when we go to do calculus on this thing, we're going to split it up into this, and do calculus on this, and do calculus on this. Okay? So I'm kind of front-end loading It doesn't have anything to do with today, but it has something to do with later on. All right? Any questions on example number 7? All right, let's do example number 8, and then we will be done. And then you guys can do your homework. Now remember, your total homework for 1.2 is due on Monday, both sections, which I found my stapler, yay. And so what we'll do is we'll take the first section and the second section, staple them together. That way I only have to grade it once. That way you only have to worry about handing it in once. All right? So for example number 8, we're going to talk about composing functions. Now, a composition or a composite of f of g. So if I say function, I wrote that down wrong. If I say f of g of x, we talked about this a little bit. I'm going to plug a function into a function. So if I was asked to write, well, let me write down what f of x is. So f of x is equal to x minus 7 in example number 8. And then I'm going to write a different color for g of x. So we'll say that g of x is equal to x squared. Okay, now watch what I'm about to do. I'm going to say, can you tell me f of g of x? Sure. Well, what is f of something? Well, we said that f of something was really that something minus 7. Right? Because here I have an x in parentheses, and here I have an x, so I could put that in parentheses, right? So f of g of x would be g of x minus 7. Do you guys see what I did there?
Oh, yeah.
Now what's g of x though? X squared. So what I'm really trying to do is figure out what is f of x squared. So if I write that all in one color, what I would be saying is that the composite function of f of g is equal to x squared minus 7. And this is written several ways, so let me give you some of the notations. This could be written as f o g. That's how I say it. But really that's shorthand for f of g. Okay? And so I guess to prove to see if that's true or not, what we could do is actually pick out a number for x and plug it in. So let's do that. Let's evaluate f of g of x, which we say is x squared minus 7. And let's let x equal 2. So then what we're saying is f of g of 2 is equal to 2 squared minus 7. So over here, I'm going to say 4 minus 7, which is negative 3. So I'm evaluating f at a certain number. Well, what is g evaluated at 2? Well, remember that we said that g of x was equal to x squared. Well, that means that g of 2 would then be equal to 2 squared, or 4. So this next term should really say f of 4. Well, what is f of 4? Well, f of 4, remember that f of x was equal to x minus 7. So then if I were to write down f of 4, then that will mean 4 minus 7, which equals negative 3. Put your thinking caps on. How many of you guys totally get this? It's okay. If your hand's just a little bit up like that, that's all right.
8.5.
8.5 out of 10, that's good. We'll do a lot of this stuff. We need to get a firm foundation in this, because in order, so calculus is the study of rates of change, changing rates of change.